So let's have a think about, with more detail now, why exactly fission and fusion are going to be releasing energy in terms of binding energy. So actually, fission and fusion do not always have to release energy, only when the conditions are right. So to understand this better, let's consider an example of fusion that will release energy. So we can go from hydrogen to helium. We can go all the way up to there, right? So we go from a lower binding energy, we go from 0 binding energy to a higher binding energy, right? And let's see why that will release energy. So we can see that our energy is equal to binding energy final, or the delta E is equal to binding energy final minus binding energy initial. So what's our binding energy final? Well, it's going to be 7. It's going to be 7 times 4 because it's 4 nucleons. And my initial binding energy was 0 times 4. So we can see that there's a positive gain of 28 mega electron volts. So in this process of going from hydrogen to helium, I am going to be gaining or liberating 28 mega electron volts. It also means that my helium will weigh a bit less. So whenever we go from a lower to a higher binding energy per nucleon, we will be losing energy. We'll be losing energy and so we'll be able to harness that. Similarly, if we were to go from uranium-235 to something lower, like for example, I think krypton somewhere here, barium somewhere there, not too sure. In this process, we're still going to be liberating energy as we go towards a higher binding energy per nucleon. I can show you. So for example, we can say that again, delta E is equal to binding energy per binding energy final minus binding energy initial, which is going to equal to 235 times let's call that 7.3 minus the binding energy. Oh, sorry, that's the initial. Sorry, our initial binding energy is that of the uranium. And the final binding energy is that of the krypton and the barium. So let me grab those values for you. So we can see that in this process, we're going to be liberating 193.45 mega electron volts. So in this process, we're going to be generating a lot of energy. Whenever we go from a lower to a higher energy, we'll be generating energy. Now, conversely, and as a rare case, we could also consider going backwards. So for example, we could consider what happens if we fission helium into hydrogen. What if we break apart helium? Well, we can try that as well and see how we go. So we can say that delta E is equal to binding energy final minus binding energy initial. And so what's our final binding energy? It's going to be that of, well, 0 times 4, because it's all hydrogens, minus my initial, which is going to be 4 times 7. So there's going to be negative 28 mega electron volts. So if I was to fission helium back into hydrogen, I'll need to put in 28 mega electron volts. So yeah, if you go from a higher to a lower, you lose energy. If you go from lower to higher, you gain energy. And so generally what we do as human beings then, so stars try to convert hydrogen into helium. Human beings have been trying to do this with making a fusion reactor for some time. I believe that recently they succeeded. Nuclear bombs turn uranium again into krypton and barium and other things like that. Going into lower, we release energy. And you can also see here that we don't really release quite as much from uranium to krypton and barium. When we do fusion, it's way more. That's why fusion is quite exciting. But anyway, thank you so much for your time, and I hope you guys enjoyed. See you guys next time. Bye. We offer physics, chemistry, and math tutoring. For more insightful explanations like this one, head to tutorgum.com.